Dear students, welcome to PHY 367. Today we are going to discuss Microcanonical Ensemble. Actually, we have discussed this ensemble before when we were discussing the phase space with fixed energy. So today we will elaborate on this and do some examples related to this. So let's give a quick recap what we have already discussed. So we already discussed that for a system which has fixed energy with a fixed energy or a system with its energy between a certain range. E and E plus delta E will fall under the definition of microcanonical ensemble. So in this case, the system might be treated as an isolated system. The system may be treated as an isolated system so that it can exchange nothing with the environment. So we have a system such that it has an insulated boundary and a fixed energy E which it cannot change. So when now we are talking about ensemble, so ensemble stands for a collection of such systems, collection of many such systems like this which are insulated from one another, but the microstate of that system would be represented by any one of these systems. So we have like for example, if we have 10 such systems, then each system represents one microstate of a larger system. So when we were discussing micro and macro states, so I made this definition very clear that what you mean here by a microstate. So in case of microcanonical ensemble, so each such system, it represents one microstate of the system, and actually there would be like tens and millions of such these systems. So in the canonical ensemble, the complete state of the system may be described by a large collection of systems like these, or system like this, I would say, each an insulated one, and having a fixed amount of energy. E, for example. So to study this system, we need to get the total number of states of this ensemble. So first I need to clarify one more thing, why we are using this ensemble terminology. That is really necessary to know. So why we need such a system. So basically there are three kinds of systems we can study. So basically there are three types of ensembles that we are going to study. So first one that I already mentioned is this microcanonical ensemble. Second one is canonical ensemble, and third one is the grand canonical ensemble. So these three kinds of ensembles are basically, these are conceptual or theoretical models which treat different bigger or larger systems which contain many number of particles, like say all of these deal with the particles of the order of 10 raised to the power 23, or the number of particles which are contained in 1 mole of any substance. So what is the difference between these three systems is that each has different kinds of parameters that we can apply to them and then study the respective system. For example, as I already told, so in case of microcanonical ensemble, we take it as insulated and we say that its energy is fixed. In case of canonical ensemble, we will say that now they can interchange energy, but we say that temperature is fixed. Energy, in canonical ensemble, different systems can interchange energy with one another, but the temperature of each system will not change. And for the third system, we can say that for grand canonical ensemble, we say that they can exchange energy. The system in this terminology, they can exchange energy as well as the number of particles. And there is another thing that is associated to these ensemble treatments, that these are not actual physical systems that we are studying. So individual system in each case is a physical system that we are studying, but this ensemble thing is only theoretical thing. It is not something that we will be dealing in our daily lives. We will never see a microcanonical ensemble or canonical ensemble or a grand canonical ensemble. So these are theoretical treatments of the real world systems. So we apply different kinds of parameters and we study them, and we call each treatment some kind of ensemble, as I mentioned already. So never anticipate that you will encounter any kind of ensemble in real world. Why we are using ensemble? Because we are dealing with large number of particles. 10 raised to the power 23 is a huge number. So the problem we face in real life that we cannot measure the physical properties of a system using the properties of each atom or each ion in a system. So what we do, we average the different properties out, and we use probability theory to calculate their macroscopic properties such as heat capacity or temperature or such and such, and we use these kinds of treatments. So first treatment we are starting with is the microcanonical ensemble, and you should just remember that we are keeping the energy fixed. So each system in microcanonical ensemble is an insulated system. Its temperature may change, but its energy will not change. So what is the advantage? We will see that each of these treatments is basically equivalent, but the methodology that we use in each case is different. So in microcanonical ensemble, the first case, the methodology is that the first step that we do is to create the or to determine. So in microcanonical ensemble, the first and foremost thing that we do is to determine the total number of accessible microstates. So first thing we will do is we need to do is that we will determine how many microstates, accessible microstates, the system has. So we usually represent it with omega. We have already done this thing in our previous lectures. So we need to determine what is omega of E. And this is the case when we have a fixed energy. And in case of some systems, we actually determine this omega of E. So we will utilize this thing when we will do certain examples. And if the energy is not fixed at some definite point, but it is actually in between some range. So if energy in another scenario, when we don't have fixed energy, when we do not have fixed single value of energy, but a range of energies, that is between E and E plus delta E. Then what we do? We calculate the phase space volume. Which phase space volume? कौन सा volume होगा? That would be accessible volume. That actually we tried to calculate, or we mentioned at least in the previous lecture. So that is again we write it like this: E in the range of delta E, and that is some integrals n e cube r and e cube e. So this is just a notation, this is not actual volume, but if we encounter such situation, then we will definitely use this formula to calculate our accessible phase space volume. And then that would also come under the treatment of, because we have now energy fixed in some range, so that comes also under the treatment of microcanonical ensemble. And now actually everything that we do in statistical physics, it has to have some kind of meaning associated with it. So what is the relationship or connection between thermodynamics and microcanonical ensemble? That we need to learn before we go into details or we do any examples of this. So just remember, everything theoretical has to have some connection with the real world. So if we do now microcanonical ensemble, this is a theoretical thing that we only do on paper or in our calculations. So for example, if you write now entropy, and entropy in thermodynamics is a real world thing. So it's a function of energy, volume, and number of particles. This is a real world thing. We can actually measure it. And if we now want to calculate this thing from microcanonical ensemble, so we have to use the Boltzmann distribution of entropy, that is kV log of omega, and that omega is now a function of energy, and this omega comes from our microcanonical ensemble. This omega is directly coming from our microcanonical ensemble. But how do we actually do this process? So for example, now we are calculating omega of E, but we have to calculate this thing that okay, omega of E or log of omega of E in a certain way that this relationship is valid. So it's not an arbitrary thing that okay, we calculate omega E and that then if we say that okay, kb log of omega E would be entropy. No, that would not be the thing. So we have to calculate omega of E or log of omega E in such a way that it has some connection with the real world thing, or we can call it that also a macroscopic property. Macroscopic property. So the connection between these two things, S and log of omega E, the connection between these two is established by a certain thing that we know as we know at this as thermodynamic limit. So these two things are connected via thermodynamic limit. I call it TDL. And what thermodynamic limit is, it says that the number of systems we are treating in any of the ensembles basically, but now specifically we are talking about microcanonical ensemble, that number of systems or total number of accessible states. Total number of states should be very large, or in other words, total number of atoms must be very large. So what we, how do we say this thing in in statistical physics? We say that n approaches infinity. And if n approaches infinity, we have to put another limit. The volume of the system, overall system, would be very large. That also should approach to infinity. And as a result of this, the particle density n over v is a constant. So this is called the thermodynamic limit. These three conditions. We are dealing with a very large system which has very many number of particles. It has huge volume overall of all particles, so that the ratio between number of particles and volumes, which is called basically particle density, is also constant. So this is the connection between statistical physics and the macroscopic properties such as entropy and heat capacity. There is a certain advantage also when we do this kind of thing. So if we take n very large and n over v constant, so we are making system, if we take n over v constant, then whatever property we measure, it will not depend on the size of the system. So we will divide, in the thermodynamic limit, we will divide entropy with the number of particles and take number of particles very large. So we will get the properties in the form of per particle. So this is now small s, which is entropy per particle, and we will also calculate other properties per particle, so that the system size does not matter. When we normalize this thing now, so the system size does not matter. So we will calculate this thing for whatever type of system, it will give us the same kind of properties. So this is very nice in terms of thermodynamics. So we can compare different the same property measured at different places or at different locations, and the results can be compared with one another. This is the one advantage. We will use this kind of limit, dividing with the total number of particles with other quantities such as heat capacity. So now we will be measuring heat capacity per unit per particle, C over n. So we will denote it with small c. So that is, now this is heat capacity per particle. And this limit has another advantage. What is that? The limit n approaching infinity has another advantage. So for larger n, we know that the omega of n, omega of En, we now call it, becomes a Gaussian function. That we discussed in when we discussed the sharpness of multiplicity function. So this is our multiplicity function. No? Remember that lecture. So this is our multiplicity function basically. And we are treating n very large, so this becomes a Gaussian function. And what is the advantage of Gaussian function? So the advantage of Gaussian function is that the fluctuations in a Gaussian system vary as 1 over square root of n. So you see here, fluctuation means the properties which deviate from their equilibrium value. So I just mention it here. So fluctuations basically signify the deviation of a property from its equilibrium value. So if we have now large number of particles n and fluctuations are varying inversely with respect to n, then for large enough systems, that is for systems in which n approach infinity, the fluctuations will also be very small. So there is another advantage of the equilibrium of taking the large number of particles, that the system is always in equilibrium and we are always calculating the equilibrium properties of that system. So now I outline various steps that we gonna use for the calculation of various properties using microcanonical ensemble. The steps to be followed to use microcanonical treatment microcanonical ensemble treatment. Okay, so I just correct it. So what we do for the first step is to determine the Hamiltonian of the system. The second step would be to determine the multiplicity function. omega, which would be a function of E, V, and N. Everything would be fixed using that Hamiltonian. And the third would be find entropy. Entropy is S equals kV log of omega. And the fourth step would be apply the thermodynamic limit the limit is n approaching infinity, and the last step would be using this treatment to calculate or determine the various properties thermodynamic properties. Such as entropy, heat capacity, and etc. So I will stop here for this lecture, and in the next lecture what we will do is we will use these steps that I have outlined here to do a couple of examples inside the microcanonical ensemble treatment and see how it works out for us. So till then,